name is Dr. Esther Trufan, and in this video, I'm going to explore another application of a calorimeter. Calorimetry is a technique that we use to measure the heat exchanged between two chemical or physical processes. And in order to do this, we use a device called a calorimeter. The most common calorimeter that we find in the chemistry laboratory is the coffee cup calorimeter. This consists of two nested styrofoam cups to ensure an insulated environment, which is also covered by a lid to ensure that no heat is exchanged between the system inside the calorimeter and the environment that is outside of it. A thermometer is part of the setup because we need to monitor the temperature changes during the process, and a stirrer or some kind of approach that ensures the homogeneity of the temperature inside the calorimeter is also useful. If we have this insulated environment, then we can say that the heat of the process is going to be the same as the heat of the water. It will simply go in the opposite direction. Therefore, if water is absorbing heat, that heat can only come from the process or reaction that is also contained within the calorimeter. Here is one example in which we are utilizing a calorimeter and the temperature change associated to the water that was placed within to determine the enthalpy of fusion of ice. For this experiment, we only need water and ice and a calorimeter. It comes with the assumption that our ice is at 0 degrees Celsius, and that 0 degrees Celsius is both the temperature of the inside and the outside of the ice. The first thing that we have to do is place our different temperatures for the water and the ice on our heating curve, because this will allow us to determine in which direction the heat is exchanged. First, we start with the water. The water starts at 25 degrees Celsius and it cools down to 12 degrees Celsius. So it goes from higher temperature to lower temperature, which means that the heat associated with this is going to carry a negative sign. For this calculation, we say that the heat of the water in the liquid phase is equal to the mass of the water, which in our case, it's 100 grams, times the specific heat of water, which is 4.184 joules per gram Celsius, times the temperature change, final temperature, 12 degrees Celsius, minus initial temperature, 25 degrees Celsius. This gives us a heat of the water of minus 5,439 joules. In the second step, we can determine the heat of the ice. If the heat of the water was minus 5,439 joules, then the heat of the ice is going to be the opposite of the heat of the water, or 5,439 joules. Because we are moving from ice at 0 degrees to water at 0 degrees, and from there to water at 12 degrees Celsius. In the final step, it is time to determine the enthalpy of fusion of ice. For this calculation, we need to remember that we are working with a two-step process or two heating components. First, the ice will need to be melted, and then the water at 0 degrees will have to be warmed up to 12 degrees. And we know the combined heat available to do all of this. We have the heat of the ice be 5,439 joules. This will be one side of the equation. On the other side, we have the two components. It is going to be the heat of the fusion plus the heat of the liquid ice warming from 0 to 12 degrees Celsius. So let's put all of that together. We have 5,439 joules equal to, for enthalpy of fusion, we will need to know the number of moles. So if we had 15 grams of ice or water, first we have to convert it to moles. And we say 1 mole of water is the same as 18 grams of water. Then we multiply by the enthalpy of fusion, which we don't know, so we keep that as its symbol divided by the 1 mole of water. So that is one piece of our puzzle. Then to this, we add the heat required to warm up the water, now from 0 degrees to 12. So we start with the 15 grams of water. We multiply it by the 4.184 joules per gram Celsius, and then we multiply it by the temperature change. Final temperature is 12 degrees Celsius. Initial temperature is 0 degrees Celsius because that's what we had as the coldest water available. From here, we simply need to do our calculation. To determine the heat associated with the warming of the water, we have all the values available here. And that is going to be 376 joules. So we have 5,439 joules be equal to, if we use the units available here, we have 0.833 moles of water times the enthalpy of fusion plus 376.2 joules. If we subtract 376.2 joules of heat from both sides, and then we divide both sides by 0.833 moles, then we find that our enthalpy of fusion is going to be equal to 6,076 joules per mole. If we convert this to kilojoules, then it will be 6.076 kilojoules per mole, which is fairly close because the literature value is 6.01 kilojoules per mole. Another type of problem that we could have is starting with a piece of ice that is not at 0 degrees Celsius, but rather colder. Think it just came out of the freezer. In that instance, the first step that the ice will have to do is warm up to 0 degrees, then it will have to melt, and then the molten ice, or the coldest water, will have to warm up to the final temperature of the mixture that we have in the calorimeter. So in this case, the water, which starts out at 25 degrees Celsius, is going to cool down to 11 degrees Celsius. From here, we can calculate the heat associated with the water by recognizing that if we have 100 grams of water that has a specific heat of 4.184 joules per gram Celsius and undergoes a temperature change of cooling to 11 degrees Celsius from 25 degrees Celsius, then the associated heat will be minus 5,758 joules. Once we determine the heat that the water emitted, which is 5,758 joules, we can move on to the second step and determine the total heat available to take the ice from minus 15 degrees Celsius all the way to plus 11 degrees Celsius in the form of water. So the heat of ice is the same as the heat of the water with a negative sign. So it will be minus 5,758 joules, giving us a heat of ice that is positive 5,758 joules. Now we're ready to calculate the specific heat of ice. It is a three-step process, and the heat of ice that we just identified here is going to be the sum of the three steps. On the left side of the equation, we're going to have the total heat that we're going to use up for the ice to undergo all these transformations, and that is 5,758 joules. On the right side of the equation, we are going to have three components. First, the ice will need to melt, and so we're going to address the heating of the solid ice. We start with 15 grams of ice. We multiply it by the specific heat of solid water, which we don't know yet. And then we multiply by And this is where it is important that we remember final minus initial. And the hottest ice that we can make is 0 degrees Celsius. And the original temperature of the ice was minus 15 degrees Celsius. In the second part of the equation, we need to address the melting of the ice. We start with the 15 grams of ice or water in the solid state. We convert it to moles. We say 1 mole of water weighs 18 grams. Then we multiply it by the enthalpy of fusion. For each 1 mole of ice melted, one needs to consume 6.01 kilojoules of heat. But because the left side of the equation has the energy in joules, we have to convert from kilojoules to joules. So this is part number 2. And for part number 3, we have to address the heating of the water from 0 degrees Celsius all the way to 11 degrees Celsius. So we have 15 grams of water at 0 degrees Celsius. Because now it is a liquid, we multiply it by the specific heat of liquid water, which is the 4.184 joules per gram Celsius. And then we multiply it by the temperature change, final temperature, 11 degrees Celsius, minus initial temperature, 0 degrees Celsius. And from here, on the left side of the equation, we have 5,758 joules. On the right side of the equation, we can simplify the first part and say we have 225 grams times degrees Celsius times the specific heat of our solid, plus the heat required to melt all the ice can be calculated because we have all the information available. It will be 5,008 joules. And in order to warm up the water from 0 degrees to 11 degrees Celsius, we are going to require 690 joules. From here, we can move all our known numbers to the left side of the equation. And we find that on the left side, we have 49.24 joules of heat available to get our 225 grams times degrees Celsius times the specific heat of our solid. From here, we divide both sides by the 225 grams times degrees Celsius, and we find that the specific heat of solid ice is 0.219 joules per gram Celsius. This is quite far from the literature value, which tells us that it should be 2.09 joules per gram Celsius. Well, let's hope that this was an experimental error, and the next time someone performs this experiment, they will be a little bit more careful with their temperature measurements.